a security researcher with Ptacek. I'm going to be presenting today about cracking WEP keys. So this talk is about some software that I developed to crack some WEP keys. It performs dictionary attacks against the WEP key generators. It does dictionary attacks against raw keys, and also performs a brute force against one of the generators. I'll describe in a bit what these generators are and what I mean by raw keys. The work I did, besides implementing cracking software, I also did a little bit of looking at the key generators themselves, and we'll go into some of that detail in this talk. One thing that this talk is not going to cover is any new form of cryptanalysis on WEP. There's several other papers out there on good research that did cryptanalysis against WEP. For those of you who saw Ian's talk yesterday, that's a very good example. Another thing I'm not going to be talking about is any sort of dynamic keying. There are some proposals out there for dynamic keying with WEP, such as 802.1x. I haven't looked at any of that yet, so I'm not going to be discussing any of that. So this is what my talk's going to look like today. First, I'm going to talk a little bit about why we should even think about cracking WEP keys. Then I'm going to go into some of the background material by giving an overview of what the WEP protocol looks like. Then I'm going to talk about how WEP is usually keyed. Then I'll talk about the WEP key generators themselves. Finally, I'll present the design of the software that I wrote, and then I'll give a little bit of results, and I'll talk about some related works at the end. So why should we perform dictionary attacks against WEP? Security is a weakest link phenomena. Your security in your system is only as good as your weakest link. And key cracking attacks the human problem. As good as the system is, if humans are using the system incorrectly, then that's where the weakest link is going to be. And for those of you who saw Ian's talk yesterday, you might wonder, but isn't WEP already broken? Why should we even bother trying to attack it from a new approach? Well, it turns out that key cracking is often a simpler attack to implement and easier to perform. It also can be less time consuming. It does have the property that it's not guaranteed to give you any success. But in the case that it does, it usually gives you results much quicker. Another interesting feature about key cracking is it actually recovers the keying material rather than any sort of a byte stream that's generated from the keying material. So this is a lot easier to use with off-the-shelf software, such as the drivers that come with WEP cards, with 802.11 cards. So what exactly is exactly is WEP? WEP is also called wired equivalent privacy. It's the piece of the 802.11 protocol that's supposed to give security to the system. As its name implies, the purpose of the protocol is to bring the same level of security to the wireless networks as exist in wired networks. It provides authentication features. It also provides encryption of the traffic. The encryption is based off of the RC4 algorithm with 64-bit keys, although there is a variant that uses 128-bit keys. The authentication primitives are built on top of the encryption primitives with a standard challenge and response type of protocol. So I'm going to give a quick overview of what it looks like to encrypt and decrypt WEP packets. Before you start, you have an unencrypted packet, which I have represented by the 802.11 frame on the left-hand side, which consists of a header and a payload. The first thing that happens in the process of encryption is the payload, a checksum is computed over the payload. This is a 32-bit CRC checksum. And when it's finished, this value is appended to the payload to form what you see on the right, which is the payload, followed by an ICV. The ICV is another word for the checksum. In the next step, a key is selected. WEP supports 4 keys that are keyed into the system, and I'll talk later about how they are keyed into the system. And when a packet is to be sent, one of the 4 keys is selected. It's completely up to the implementation how these keys are selected. But what happens is a key number between 0 and 3 is generated, and are used to index a table, which you see as the 4x40 box in the middle, which has 4 40-bit keys, and out of that you get a single 40-bit key. In the next step, an IV is selected. This is just a value that's going to be used as part of the encryption. The standard also doesn't mandate anything about how the IV is to be selected, so this is completely up to the implementer as well. The IV is a 24-bit number, and after it's selected, is prepended to the key number that was used to select the key earlier to form a 32-bit value. In the next step, an actual encryption operation is performed. An RC4 key is formed by taking the initialization vector, IV, and appending it to the key. If you remember, the IV was 24 bits, and the key was 40 bits, so the total key size here is 64 bits going into RC4. That key is used to encrypt the payload and the ICV. And out of that, of course, you get the encrypted payload and ICV, which is shown in red on the side. And finally, we construct the frame that's going to be sent out over the wire. This is done by taking the encrypted payload and ICV, prepending it with the IV and the key number, and then popping a header on the front of that. The decryption process is pretty straightforward from the description of the encryption process. The first thing that's done is the key number from the frame that was sent, which is shown in blue right after the IV there, is used to index the table of keys again. And this is used to select another, the 40-bit key on the receiver side. Next, that key number is attached to the IV, which was also in the header, and used as a key to RC4 to decrypt the payload and the ICV. And out of that, of course, you get the decrypted payload and ICV. In the next step, the checksum is again computed over the payload to get ICV prime there on the side, which is a 32-bit number, and that number is compared against the ICV in the transmitted packet. This is done to verify that the packet was indeed decrypted properly. And at the same time, the actual unencrypted frame is formed by popping a header onto that. WEP also provides authentication. The authentication is based directly on the encryption primitives. It is done by having the access point generate a nonce, which is a random value, and sent in plain text to the client. The client takes the nonce and encrypts it and sends it back to the access point. And then the server decrypts the response and compares the nonce against the one it sent. If it was the same nonce, then the access point believes that the client actually has the key and is authenticated. One thing that's important to note is authentication is not a mandated feature of the protocol. You can use WEP without having the authentication option turned on at all. So as I mentioned earlier, there's actually another variant that instead of using 64-bit keys, uses 128-bit keys. It's almost identical to the 64-bit variant that we saw earlier. The purpose of this variant, of course, is to increase the key size. Yes, go ahead.
What you're saying is that we use the 40-bit keys and we append to it or append to it 24 bits random number, which is then set fusions.
No, the 24-bit random number it's not necessarily random, but the 24-bit IV was sent in the plain text. The key was never sent.
No, the key was never sent.
Right.
Basically, we're only on the 40-bit.
Yes, the key that you enter into WEP when you key the system is a 40-bit key. The key that's used in RC4 is a 64-bit key, so there's a little confusion there.
Yeah, and if I want to brute force, I only need 40 bits.
Yes, exactly. Okay, so this the 128-bit variant, the purpose, of course, is to increase the key size. I guess they were hoping for stronger security. The 128-bit variant is non-standard, but it is in widespread use, and all the people who implement it the same way for interoperability. all the encryption steps that were outlined earlier are almost exactly identical, except for in the key selection, a 104-bit key is selected instead of a 40-bit key. And then during the encryption process, when the IV and the key are concatenated together, the resultant RC4 key is actually 128 bits long, which is shown here in the diagram. So where do these keys come from? The WEP standard, the 802.11 standard itself does not mandate how the keys are to be distributed or set on the system. In practice, what happens is keys are manually distributed, which means somebody comes up with a key, walks over to somebody else and hands them the key or tells them to it over the phone. Keys are also statically configured. They're not dynamically set by any sort of protocol. Somebody goes and manually enters them into the computer. These two items have implications. Because keys are manually distributed and statically configured, chances are they're going to be selected to be easy to remember so that somebody could tell it to someone else, remember it, and enter it into a computer easily. Also, chances are they're not going to be changed very often. If you have 100 users who are using a system with a statically keyed key, then to change it, you have to contact each of those users and have them all change them at the same time. That's not very practical. As was pointed out earlier, there are 4 40-bit keys that are used for the 64-bit variant. In the 128-bit variant, I've only seen in implementations that have a single key that's 104 bits long, but I don't see why someone couldn't support also having several keys there. The key values can be entered directly as hex. What this means is you have a dialog box that has 40 boxes, and you can enter in 40 hex values there. But since humans don't generally like to enter in a lot of hex values, implementers have been kind enough to provide a key generator. There's actually 2 key generators, one that's used for the 64-bit variant and one that's used for the 128-bit variant. The purpose of the key generator, of course, is to enter in an ASCII string, which is much easier for a human to deal with, and to turn that string into the keying data that's required. Again, these key generators are not standard. They're not specified in the 802.11 standard, but they are in widespread use. And again, for interoperability, everybody has implemented the same key generators. So to give you a concrete example of what this might look like, on the bottom of the screen you can see 40 boxes where hex values can be entered into, and you can see why people generally wouldn't want to do that. That's a lot of work. And you can see above it where there's a box for a passphrase to be entered in, and I've entered in my passphrase. And the hex values on the bottom, if you can read them at all, were the values that were generated from the phrase my passphrase. So what do these generators look like? I'm going to go over this a little quickly at first, and we'll come back to some of these points. This is what the 64-bit generator looks like, this diagram at the top. It's composed of several steps. The first step is a folding operation where the passphrase is folded down into a 32-bit number. And this is done in the following manner. All of the letters from the passphrase are laid out, where you can see in this section right here, 4 across until all of the characters are used. And then an exclusive OR operation is performed down each column. So in this example, the value that I'm pointing out right there was generated by performing the exclusive OR of the letters M, A, H, and E. Likewise, these other 4 values at the bottom were the result of another exclusive OR operation with the other columns. So once the 32-bit value is generated, this is used as a seed to a pseudo-random number generator, which is shown in the box. The type of pseudo-random number generator used here was a 32-bit linear congruential pseudo-random number generator, and we'll see why that's important in a few seconds. This generator spits out 32-bit numbers. You can see a bunch of them on the side there, where the top number would be 34, F8, A9, 27. The generator is used to generate 40 different values. From each of these 40 values, 1 byte is selected, and those are the boxes shown in green there. And this is used for the keying material. So in this example, the key would be F8, 61, A3, E7, C3, 8E, and so on. Okay, so this is a really, really bad key generator. Why is that? Well, ideally, since we're generating 4 40-bit keys, we'd like to at least have 40 bits of entropy. So we at least have entropy enough for one of those keys. But this generator reduces the entropy in several ways. In the first step, where the ASCII key is mapped down to a seed, we reduce, well, right off the bat, we took a string which could have had an arbitrary amount of entropy in it. We mapped it down to a 32-bit value. Already we have at most 32 bits of entropy. In the next step, where we actually did the exclusive OR of the characters, it's important to note that since these characters are ASCII, all of their high bits are 0. When the exclusive OR operation is performed on these values, the resultant value is also going to have a high bit of 0. So of these 4 characters that were of these 4 numbers that were generated to form the 32-bit value, 4 of the bits are always 0. So now the entropy is at most 28 bits, or 32 minus 4. Or said another way, only the seeds of 00, 00, 00, 00, 00 through 7F, 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 7F can occur where all the high bits are always cleared. So next, the way that they use the pseudo-random number generator also reduces the entropy. So in this step, remember that there was 40 values generated from the generator. From each of these values, only one of the bytes was selected. Well, the generator is a linear congruential generator, and it uses a modulus of 2 to the 32. This type of generator has the property that the least significant bits are much less random than the most significant bits. In particular, if you look at the lowest bit, it will cycle every 2 iterations. So if you pull 3 numbers from the generator and look at only the lowest bit, the 3rd bit that you get out will be the same as the 1st bit that you get out. And also, if you look at the 4th bit, it'll cycle with a cycle length of 16, or 2 to the 4th. And so these values that we're pulling out from bits 16 through 23 have a cycle length of 2 to the 24. Or said another way, for this generator, only the seeds of 0, 0, 0, 0 through 0, FF, FF, FF will result in unique keys. All the other seeds that are used will give you the same result as one of the seeds in this range. So right there, the entropy can be at most 24 bits. Now when you take these effects all together, the net result is the entropy of this generator is only 21 bits. In the first ASCII folding operation, we noticed that we could only the seeds of 0 through 7F, 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 where the high bits were always 0, could be generated. And then in the random number generator, we noticed that only the seeds 0 through, this is incorrect, it should be 00, FF, 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 will result in unique keys. When you combine these 2 facts, we note that we only need to consider the seeds 0 through 0, 7F, 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 or 2 to the 21 seeds. So this is a pretty small number. 2 to the 20 is about, what is that, 1 million? So this is about, what, 2 million values? I think I'm doing my math right. But not a whole lot of values, at least. So like I mentioned, there's a separate generator for the 128-bit variant. This generator is a bit better. It's based on the MD5 algorithm. The purpose of this generator, of course, was to map an ASCII key to a 104-bit key value to use with the 128-bit variant. This is done in several steps. In the first step, an ASCII string is extended to 64 bytes through repetition. So in the example where the passphrase was my passphrase, the 64 bytes, the description underneath that should read bytes, not bits, would be my passphrase, my passphrase, my passphrase, my passphrase, and so on until you reach 64 characters. It's not really clear why they performed this operation. It seems to indicate that they didn't really have a good understanding of how MD5 worked. In the next step, the MD5 of this buffer is taken, which results in another 64 bytes. And of this, only the first 104 bits, or 13 bytes, are used, which is shown in the green there. So this generator is actually pretty good. The key strength relies on the strength of MD5, which so far has a pretty good record, and the entropy of the string that's entered. And this is the property that we like to have in a key generator. So now I'm going to change gears a little bit and start talking about the WEP cracker that I implemented. This cracker is a proof of concept program. I didn't bother going to all the little bells and whistles that you could put into a cracker. I'm going to leave that for someone else to come along and do afterwards if someone really wants to do that. This program will perform dictionary attacks against WEP keys, and what that means is it will go through a dictionary and try every single word in the dictionary to see if it's a valid key. It can find keys that were generated from the dictionary word going through one of the key generators, or it can find keys that were entered as hex values but actually are ASCII strings. It also has the feature to perform a brute force on the 64-bit WEP generator, which I showed earlier was weak. It doesn't have any support for any of the other brute force attacks that are possible, and I'll discuss why towards the end of the talk. So this program is organized as follows. There's a component which collects a bunch of packets which are used to actually perform verification. That's shown in the blue at the bottom. Then there's a part of the program which generates guesses. These guesses are then turned into keys through another section of the program which maps guesses to keys. Finally, these keys are used to try to decrypt the packets which were previously collected and to print out success when one of the keys was actually successful. The packet collector component has the purpose that it needs to collect packets to be used for verification. The implementation that I made only collects 802.11 data packets. It doesn't bother with any of the other types of packets, and I'll discuss why in a little bit. And this part of the program currently collects 2 packets, and I'll also describe why we wanted 2 packets. The program was kept simple by using PCAP format files. There's no actual packet capture built into my program, but rather I'm using other programs such as the Prism Dump utility to collect packets. Prism Dump saves the packets into a packet file in the PCAP file format, and then I read them in and perform the cracking operation. This made the design a lot simpler. It also allows for offline cracking where packets are captured, stored onto disk, and then cracked at your leisure. In the next section, making guesses. How do we make the guesses that are used for used to guess the key? Well, there's 2 different modes to this program. There's the dictionary attack mode and there's the brute force mode. In the dictionary attack mode, we read a bunch of words from a file. It's kept really simple. Again, there's a lot of room for improvements here. For example, programs such as Alec Muffet's Crack have really nice generator sections that will perform operations on the words to transform them into other words, to append letters to them, to change regular words into elite speak or something like that. I leave it to somebody else to add functionality like that if they desire to. For the brute force attacks, what we want to do is generate a bunch of seeds. We don't want to generate actual words. We want to generate the seeds that are going to go into the pseudo-random number generator. And as I described earlier, we want to generate the seeds from 0 through 7F, 7F, 7F. So once we have these guesses, we have to turn them into keys. This can be done in a number of ways. In the simplest operation, you can take a guess, which is a word, and transform it directly to a key by doing nothing, just using it as a key. For example, when using 64-bit WEP, you need a 40-bit key. You can take the first 5 letters of any word and use that as the key. Or for the 128-bit variant, you need 13 bytes or 104 bits. And this is either done by truncating a long word or zero filling in a short word. If we're using the key generator, we take an ASCII value that we guessed, and we run the key generation function, and we get out the keys directly. And this can be done by using the 64-bit generator or the 128-bit generator. If we're performing a brute force, we've generated seed values and not actual ASCII strings. In this case, we bypass the first operation of the key generator and provide the seed directly to the pseudo-random number generator, and then generate the bits from there. So once we have a key, we need to verify whether that key was actually the right key used to encrypt and decrypt the traffic that we've captured. There are several possibilities of how you can do this. The first and most obvious would be to look at authentication packets. Why? Authentication packets give us a known plaintext. They give us the plaintext, and they give us the encrypted results of a packet that's encrypted using that plaintext. So it would be trivial to do the comparison in this case, but I chose not to do this. Why? This is far from ideal for two reasons. One is that authentication only happens when someone comes and joins the network. So this is an infrequent operation. You could sit around waiting for hours for someone to join. Number two, it's optional, which means you could sit around forever waiting for this to happen and never get any results. So obviously this is not going to be the best way to do this. Data packets are much more common. So what can we do to use data packets to perform this verification? The first thing that came to my mind was, why don't we just decrypt the packet and look to see if it looks like a packet? This sort of implies that you know what a packet would look like. Usually I know what packets look like because usually when I'm looking at networks I see IP traffic. So you could decrypt the packet, perform a few heuristics to see if it looks like an IP packet. And if it does, you could say, well, I must have got the right key. But there's another option that turns out to work a bit better. You can decrypt the packet and verify the checksum on the packet after you decrypted it, recalling that every single packet that was encrypted had a checksum applied to it. Both of these methods have the property that they're inexact. You can decrypt a packet and it could look like a valid IP packet, or the checksum could verify properly even in the case where you actually had the wrong key. So what will you do in this case to eliminate false positives? Well, you could verify several packets. The odds of having a false positive are really low on one packet. The odds of having a false positive on several packets gets increasingly smaller. So the method I actually implemented was ICV verification. This works in the following way. You get the IV and the key number from the packet. You form an RC4 key by taking the IV and the selected key and concatenating them. You decrypt the payload and the ICV of the packet. Finally, you recompute the ICV of the payload and you perform the comparison. This was all basically the same steps of decryption that were pointed out earlier. Because we're comparing these 32-bit ICVs to verify whether it was decrypted properly, we have a probability of a false match roughly 1 in 2 to the 32, or 1 in 4 billion. I wanted a little bit higher assurance than this, so I actually took 2 packets to verify against, which gives a probability of a false match of 1 in 2 to the 64, which is very, very, very infrequent. So what are the results of this construction of this program? Well, I made the program. It exists. It performs dictionary attacks on ASCII keys, keys that were directly set as ASCII, or against keys that were generated, using the 64 and 128-bit generators. It also performs a brute force against the 64-bit generator. How well does it work? Well, the brute force that I mentioned earlier, going through all of the 2 to the 21 possibilities for the 64-bit generator, takes about 35 seconds. So pretty fast. That's about 60,000 guesses a second. Also performing a regular dictionary attack against 64-bit WEP takes about 60,000 seconds. I'm sorry, 60,000 guesses per second. Doing the 128-bit variant is a little bit slower, depending on whether or not you use the generator. The generator, you can see, slows it down a little bit, giving you a speed of 45,000 guesses a second. For the case where you don't use the generator, about 55,000 guesses per second. So what does this mean? Well, at these speeds, you really don't want to try to brute force the 40-bit key size. In the case where people aren't using the generator, you might think, well, why don't we just try all of the possible keys for the 40-bit WEP key? Well, I don't know. You could do this if you wanted to. It would take about 210 days, given the speeds of the numbers I gave you for my laptop. That's reasonable. If you had 100 machines, about 2 days to do. So, not out of the question. But we'll see why you might not want to do that in a few seconds, because there are some better attacks out there. What about brute force against 128-bit WEP? Well, the 104-bit keys will take about 10 to the 19th years. You probably don't even want to start doing that. What are the implications of this? Obviously, nobody should be using the 64-bit generator. It's horribly broken, 35 seconds to break, not very strong at all. If you're going to use 64-bit WEP, you should either use hex keys, or if you choose an ASCII key and map it directly to hex. But the same guideline should be used basically as you'd use to select any other password. You should select passwords that are strong. They shouldn't be dictionary words. Maybe not even 2 dictionary words put together. Basically, all the things that people told you about how to pick your UNIX password, you should apply that to WEP. What about the strength of 40-bit keys? They're reasonably strong. Again, if somebody has 100 computers, they can probably brute force the whole thing in a few days. Well-chosen 104-bit keys are very strong, whether or not they are generated. But before anybody gets all happy about saying, well, I picked a good key and I'm not using this generator, we look at some related work. There's more bad news. For those of you who saw Ian's talk yesterday, some of the work that he had done earlier this year, he pointed out that WEP encryption is fundamentally flawed. In other words, no matter how well you select your key, someone can still decrypt your traffic, perform injection, perform a number of attacks. The attack times for some of the attacks that he outlined are on the order of a few days, maybe a day of collecting traffic and then some processing, maybe 2, depending on the attack. There were also some other attacks pointed out by Bill Arbo. Ian had covered some of these also in his talk, pointing out that WEP authentication itself is broken too. You can perform the authentication step by observing someone else's authentication. He also extended some of the Goldberg attacks, and the net result of his extensions were that it's easier to perform. So all of this related work taken together says that if you are going to crack WEP keys, you really shouldn't bother spending more than a day or 2 on doing it, because if you have a day or 2 to spare, there's attacks that are guaranteed to give you results. So this is another reason why nobody should try to brute force the 40-bit keys. Well, that's the bulk of my talk. I have a short demonstration to give also. Before I get to that, I'd like to point out that all of the source code for the program that I just mentioned are on the CD that you have. They're also available online at the URL mentioned right there. I also have a bunch of other utilities up at that site. Feel free to grab whatever you like. If anybody has questions about any of my talk that they don't want to bring up here, feel free to send me an email at tnewsham@stake.com. All the source code is in the public domain, so feel free to use it in anything you want to use it in. And right before I get to questions, I'd like to give a quick demonstration of how this works. Okay, so in this window here, I have a couple of files that I've captured previously. The 64bit.cap is a capture of me using the 64-bit key generator, and basically all of these captures just have a few ARP packets in them, nothing really special. The 128-bit file, likewise, is using the 128-bit generator. I also have a third file there called 128-ASCII, and in this one I chose a key by picking a 13-letter dictionary word and then entering the hex values for the key directly. So let's see what it looks like when you run my program on these files. So the program is called WEP Crack, and in this first case I'm going to run it against the 64-bit generator. So I select the file that I'm going to crack, and I select a list of words. This is just the user dict words from Linux. Not the biggest dictionary you can get, so this is probably not the best example, but my word is, the word I picked was actually victimized, which is also in that dictionary. So it took all of a second to guess this, and it shows you how fast it took. And then it also shows you what the hex WEP key is if you would like to actually enter it in by hex values, and it also shows you the word that was generated from. So if you wanted to crack the 128-bit variant, you actually have to know that you have packets that were encrypted with a 128-bit variant, because there is really no way that I know of to distinguish the packets. So in this case I have a flag -S for strong 128 bits. And then I specify the captured file and the word list again. And this one started with an A, so it took a very small amount of time. The word was arrogant. There's the hex bits that were used to, as the key. Again, it tells you the performance, how fast it was going. Let's say that the 64-bit capture wasn't generated from Word, or we didn't know it was generated from Word, and we just wanted to perform a brute force. Well, in this case, you would specify -B and then the capture file. You don't have to specify a word list because it's going to brute force the whole space. This one's going to take a little bit longer because it is doing 2 to the 21 or some fraction of it. So there it took 3 seconds to go through. Obviously, it didn't have to go through the whole space, which would have taken about 30, 35 seconds. So you'll see some weird results here. It says success. It shows you what the seed was. But then it says generated by, and recall that the word that I used was victimized. But it shows you AA, semicolon, bang, KA. This is because there's a lot of collisions in the ASCII mapping. And I'm not actually using ASCII strings, but once I get a seed, I want to have something I can type into the generator. So I go back and unfold the bits to find just one of the values that can be used. So if you type that into the key generator, you'll get the same WEP key as you would have if you typed in the word victimized. It turns out that the generator has a lot of collisions, so there are a lot of words that will map to the same value. And finally, I have a file here where I used a key that was directly ASCII. So how do we crack that? First you have to specify which key you're cracking, because in this mode we'll crack each key separately. I'm using key number 0, or the first key. Also, I'm using the 128-bit variant, so I use -S. Then I specify my file and a word list. And away it goes. The word I used was unanticipated, and you can see that the WEP key below it, 75, 60, 61, those are actually the characters unanticipated. Again, it took about 0.4 seconds. That's pretty much it. Anybody have any questions about anything I covered or the program? Yes, go ahead.
How are most vendors storing the keys on the device?
Keys are typically entered in with a little, like in the example of Windows, with one of those little Windows applets, and then when you click the store key, it actually downloads the keying material into the card itself. But at the same time, they usually save a copy in the registry or something like that, so it doesn't really help them a whole lot. Yes? Am I aware of any non-broken 40-bit key generators? As far as I know, there's just the one generator being used. If people use different generators, then obviously, unless they're using the same one, it's not going to interop. So all of the commercial software I've seen uses the same generator. Some of the drivers for Linux or other systems may actually have a setting to specify which generator to use. For example, the Linux one I use has an entry where you actually tell it which program to run. So you could swap it out with anything you want. Of course, once you do that, you're not going to be interoperating with anything else. So, yes, go ahead. What kind of card do I use for packet capture? I'm currently using an SMC card. It's a Prism 2 based. Most of the software that you'll see on my website there will be applicable to that. Prism 2 is widely used in a lot of cards, so you can pick up a lot of cards like D-Link, or there's some Cisco cards that have Prism 2, but of course it's not the only chipset out there. Yes, go ahead. Do all base stations have 128-bit capabilities, is what you're asking? To be honest, I haven't really played with a lot of the base stations. I play mostly with the cards, so I couldn't really answer your question there. So the answer in the audience was not all of them have the 128-bit capabilities. Well, I guess that's it.